Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon and welcome everybody. It's my great pleasure to introduce Julie Lechner from University of Washington. Actually, I've known Julie for quite a while. We overlapped for about 3 years at the University of Washington. And now I notice on a CV, in the meanwhile, she's managed to acquire a whole sorts of fellowships, including Google, NSF, DoD ARCs, and the list goes on. So Julie's work is actually based on the observation that data now is everywhere. As Rick Rashid's TechFest talk also pointed out, data centers, sensor networks, internet, data is everywhere. But the problem with the data is it often tends to be imprecise. So what Julie's going to tell us about is what can you do with imprecise data.
Thanks.
Yeah.
Am I mic'd properly? OK. So hi, everybody. Thank you, Ratul. My name is Julie Lechner, and my talk today is going to be on my thesis work. My thesis work is a project called Lahar. And in case you don't know what a lahar is, when a snow-covered volcano erupts, like Mount St. Helens, there's this massive stream of dirt and debris that slides down the side. And we named the system Lahar because it manages massive streams of dirty data. So what do I mean by dirty data? OK. So one example of dirty data comes from speech recognition. So you take an audio stream as input, and the goal of speech processing is to figure out what are the words or the sentences that were spoken in that speech. Now, this is obviously imprecise because not only is the problem difficult, but we have language ambiguities, like was the word ate the number, or was it the verb? So what you get as the output of speech recognition is an imprecise stream of words or sentences. Another example of places where dirty streams show up is in sensor data. If you take sensors and put them on a person, like thermometers, barometers, accelerometers, et cetera, that data is not noisy. But then when you try to use it to infer what was this person doing at any given time, or where was this person in their home, that's imprecise. And so we get, again, an imprecise stream. The challenge in dealing with this imprecise data is that there's no existing framework right now for doing the types of analysis we want to on this data. So there are streaming databases that let us do rich analyses on streaming data, but they don't handle imprecise data. Similarly, there are probabilistic databases that let us do rich analyses on imprecise data, but they don't handle sequences. So the system I'm going to talk to you about today is a system that manages imprecise and sequential data. So as an example, the state of the art for speech processing is basically Google's audio called Gaudi. And what it can do is it can do single word indexes on speech. So you can go to Google and sit down and say, find me all the videos or all the speech streams that contain a particular word, like health. But if you want to find the phrase healthcare, or you want to find any phrase at all that includes something sequential, Google has a hard time with that. So what we'd like to be able to do with speech data is answer questions. Any question we can answer on text, we would like to be able to answer on audio as well. In the sensor domain, what we can do today is using artificial intelligence. We can answer things in a smart home, for example, like what was Sally most likely doing at noon today? Was she making tea? Was she eating, et cetera? We can learn these things from sensor data. What we can't do today is answer high-level aggregate queries, like not only was Sally eating or not, but maybe how many meals did Sally eat today? We have to be able to reason about meals, and we have to be able to aggregate these things together. So this is sort of where we want to go. And Lahar, the talk I'm going to tell you about today, Lahar, is going to take us across this gap. So it's going to go from low-level data all the way to rich, high-level analysis. So the running example I'm going to use today is RFID. It stands for radio frequency identification. RFID is a proximity sensor. So RFID systems are comprised of two parts, the reader, which is the white thing you see. And these are usually statically placed along hallways or in rooms. And then there's RFID tags, which are extremely cheap. And you can slap them on whatever object whose location you want to track. And basically, whenever a tag comes within close range of a sensor, maybe 3 to 6 feet, the tag is detected by the antenna, and the tag has a unique ID. And so the antenna can log the presence of the tag in a database of some kind. I'm just going to use this. OK, so RFID is used in warehouses. It's used sometimes in smart homes. And increasingly, it's actually used in hospitals. And there are many real-world deployments of hospitals using RFID in the States. And so here's Dr. Bob in the corner. And this is just a little example of how RFID works. Bob goes about his day, and he carries an RFID tag. So every time Bob's tag passes underneath one of these RFID readers, which are A, B, and C in the picture, the reader detects the presence of the tag and records that tag, both the ID and the timestamp, in a database like the one you see at the right. Now, the reason hospitals are willing to spend the money to use these, to deploy these systems, is because they're useful for real-time tracking. Where is Bob? Where is the crash cart? Very simple things. Where did this patient's chart go? But really, what we'd like to do is we'd like to use this data to answer much more sophisticated questions. So let's say the hospital's already recouped its cost, but you're an analyst in the hospital, and you've been charged with trying to save $1 million in the hospital budget. Now, even though the hospital didn't deploy the RFID to help you with this, if you've got RFID tags on all of your equipment, all of a sudden you have a huge trove of data that you can use to figure out what assets you're using, what assets you're not, and cut money from that budget. So to do that, you're going to want to ask questions like this. So how many times per day does each doctor visit the stockroom? How often is equipment borrowed from certain departments? And when equipment is borrowed from a department, what department did it come from? And how many hours per week does each wheelchair spend in the stockroom? So how many assets are underutilized in some sense? Now, these questions are very difficult to answer using this RFID data. So there's a number of reasons. So first of all, there's noise. You may have noticed in the animation, sometimes Bob's tag passes underneath the antenna, and the antenna fails to detect the presence of the tag. So the data is noisy. The data is also ambiguous. So if you look at this hospital layout, antennas B and C sort of flank the doors of the stockroom and the intensive care unit. But given these sensors, no matter how perfect they are, even with no noise, we could never tell which of these two rooms Bob or any equipment was in. So we have ambiguity. Third, there's a semantic mismatch. So the data that's recorded by the RFID system is this table that you see on the right. It's written at the level of antenna IDs and timestamps. But the questions we want to ask are written in terms of high-level semantic locations like hallway, office, ICU, et cetera. So somehow we have to map our data up into this data that we'd like to ask queries about. And finally, there's a scalability issue. If we have tags on hundreds and thousands of different people and equipment in the hospital, and we track them for 5 years, that's a huge trove of data that we want to mine. OK, so this is a semi-common problem, especially in sensor systems. And there are two state-of-the-art. There's a question.
On the previous slide, what was I supposed to get from the citation on the bottom right?
Let me go back to the slide. Oh, now we have to wait for Bob. Sorry, we can't go back to that slide. What? I don't understand your question.
There was a citation to electromagnetic interference from RFIDs.
Yes. So let's just put up the picture of the hospital. So these are just citations of RFID deployments, and there's a study that was in the Journal of the American Medical Association that basically is saying you have to be very careful about where you place RFID in a hospital. And I'm putting this here just to sort of explain that you can't solve these problems by deploying more sensors everywhere. There are physical limitations to where you can deploy these sensors that make this noise problem and these ambiguity problems inherent to the system. That's all. Any other questions? OK, so there are sort of two standard ways of dealing with this problem. One of them comes from the artificial intelligence community. One comes from the databases community. So in general, when the databases community sees data like this, their solution is to throw it in a data warehouse, a database, and perform analyses on it. So by doing that, you get what you see here. So the advantage of this is that you get flexibility and scalability. Databases are very good at scaling, and they let you answer or ask questions in high-level languages like SQL that are very easy, well, relatively easy for a layman to learn. So that's good. But we get some major disadvantages using this. We lose the high-level semantics. If we use this system, we can't ask our questions in terms of ICU and stockroom, right? We have to translate these queries into the level that our data is actually written at, which turns into something like this. So when was Bob detected by a certain antenna here, but then later not by another antenna later? This is not intuitive at all. It's not flexible. Another thing we lose is robustness to noise. So if we express our queries like this, and all of a sudden Bob is not detected by antenna B, we get brittle queries. We get answers to our queries that are incorrect. OK, the flip side approach, the approach that comes from the artificial intelligence community, is to build a model. And this model includes things like the layout of the hospital. It includes the locations of the antennas within the hospital. It might include motion patterns if it's a sophisticated model. And importantly, it includes an encoding of the query itself. So we take this model. We perform probabilistic inference on this model. It doesn't matter what kind. Pick your favorite algorithm. And the output of the model is the answer to your query. So the nice thing we get about this is that these models are built to do these two things. They're built to map low-level data into high-level semantics, and they're built to be robust to noise. So we get those advantages sort of for free. But the disadvantage is that this model is extremely inflexible. Because the query is encoded in the model, we have to build a new model every time we have a new query. So this is not only difficult to express, but furthermore, every time we have a new query, we have to re-perform our probabilistic inference, which is a major scalability problem. OK, so in case it's not obvious where I'm going with this, what we'd like to do is take these two approaches and combine them in some way. So we'd like to take the advantages from both and get rid of the disadvantages. This is where my work falls, and I'm not the only one doing work in this area. There are a couple of other people also taking the same approach. But let me tell you about my approach to this combination, which is called the Markovian stream approach. So in my thesis, what I'm suggesting we do, or what I'm doing, is we take our low-level data streams and we build some sort of model and we perform inference on that model. But the difference between this and what I just told you is that the output of this model is not the answer to our query. The output of this model is an intermediate type of data called a Markovian stream. In the hospital example, the Markovian stream represents maybe the set of paths that Bob may have taken through the building. Right? So it's not the answer to the query, it's this intermediate data type Markovian stream. Then we put the Markovian stream into a database, and we actually ask the queries to this database. Okay, so from the AI side of things, what we get by using this probabilistic inference to produce the Markovian stream is we get our mapping into high-level semantics, and we get our robustness to noise. But then by putting a database on top of this, we then get our flexibility and our scalability that are inherent in databases. Okay, so the key to this Markovian stream approach is to use the Markovian stream to decouple the probabilistic inference from the databases work, from the data management work. So for this reason, in this talk today, I'm not going to talk about probabilistic inference at all. It's an important part of how I get the data that goes as input to Lahar, but Lahar does not actually perform probabilistic inference. So you can take any data you want, perform your favorite probabilistic inference algorithm, get this Markovian stream, and then the rest of that pipeline is what I'm going to talk about today, is how do we take Lahar and process these Markovian streams.
Is there information lost in the probabilistic inference when you say like flexible queries, like when you convert like raw data using inference into Markovian streams, are you actually constructing Markovian streams with some kinds of queries in mind, or is it somehow magically completely information equivalent?
It depends on the model you're talking about. So this is not losing any information relative to the model that you perform inference on, but there are some queries that you can express as a more sophisticated model that you can't express on top of this. So in that sense, I am targeting a specific set of queries that you can answer on this materialized stream that I'll talk about later. Yes?
Just to make sure I understand. So it does seem like a domain knowledge expert would have to say, here's the feature set that I think people are going to be interested in. You know, either trajectories to the hospital or rooms visited, equipment, and then they're going to build that probabilistic inference system to extract those features, right? And then Markovian stream is a way of encoding that feature set.
Yes.
Okay.
You definitely need a domain expert to get you to the Markovian stream. Yeah. But that's true no matter what you do. No matter what approach you take, to get this high-level data out, you need a domain expert who has the knowledge to build this model in the first place. Okay, so the bottom line of this slide is that the rest of the talk is about Lahar, and Lahar is the first database that can actually manage these imprecise streams called Markovian streams. So let me give you one slide about what Lahar does. Lahar is a probabilistic database, so the input data it takes looks something like this. So these are different paths that Bob may have taken through the hospital. We ask Lahar questions like, when did Bob enter the ICU? And because our input data is imprecise, the answers we get out of Lahar are also imprecise. So for example, here you see at every time step in Bob's day, there's some probability that he actually satisfied this query, that he entered the ICU. And so if you plot those probabilities out over time, the peak of that signal is the time at which it's most likely that Bob actually entered the ICU. Okay, the key challenge to this is efficiency. So I'll explain this in a little bit more detail later, but a single Markovian stream encodes an exponential possible number of sequences, either through the building or through the audio stream, whatever it might be. And so efficiency is the really critical challenge in processing these streams effectively. Yes?
It seems to me like from a research point of view, the real challenge here is balancing efficiency versus the expressiveness of the queries that you can satisfy using this encoding of the stream that was talked about. So will you be touching on that? You know, how efficiency relative to the kinds of queries that you're allowing to be expressed and that sort of thing?
I think I understand your question, and I think I will be. So stop me later on if I'm not. There's a part in the talk where I'll talk about the different types of queries we can support. And after that part, if you're not satisfied, then can you again? Yeah.
Is a Markovian stream a well-known type of probabilistic data structure, or is that something new?
Yes and no. The term is something that we made up. This data exists. So there are all kinds of systems out there that take this low-level data, use a hidden Markov model, for example, and produce exactly this data. The problem is nobody before has tried to do further analyses on this data, and so nobody's materialized this stream, and so nobody's had a reason to call it anything. And when I explain the formal definition of a Markovian stream, I'll explain why it's called that.
I guess this might be
part of the talk that you're not going to go into, but I'm curious, in that model that you had, in that picture you had before, there was no way to determine if you went into the stockroom or the ICU. So would this say probability is a half that he's in the stockroom and a half that he's in the ICU, or is there some way to refine that to, there's a prior probability and it's 0.3 versus 0.7?
The model encodes a prior distribution over where people are likely to go. And then the Markovian stream, I don't know if you're an AI person, but the Markovian stream is basically exactly that model conditioned on the actual RFID readings that Bob saw. Okay, so this is Lahar. Here's sort of a visual outline of what the talk's going to be about, what the contributions of my thesis are. So there are several key components to Lahar. The first one is a pattern matching algorithm. So because Markovian streams are sequential, the types of questions that people like to ask include sequences, and so we do pattern matching to detect these sequences. So that's sort of the core unit of analysis in Lahar, is pattern matching. Then underneath this pattern matching, there are a bunch of techniques in my thesis that make this pattern matching effective, efficient, scalable. So how do we take these pattern matching algorithms and scale them up to large sizes and do this quickly? So that's scalability. And then on top of this pattern matching, there's a set of analytics algorithms. So the other part of the contributions of my thesis are what are the algorithms that we can provide to do not just pattern matching, but richer analyses like aggregations and drill downs and things that I'll give you examples of later. So that's Lahar. That's the outline of our talk. And before I get into that, I'm going to tell you more formally what Markovian streams are. OK. So Markovian streams are the input data to Lahar. And what they really are is imprecise, temporally correlated sequences. So hopefully this will answer the question that I had just had. When I say a Markovian stream is imprecise, what I mean is that the true value of the stream at every time step is not known. So in this example, at time t2, we're not sure where Bob was, but we know that with some probability he was in the ICU, and with some probability he was in the stockroom. So we know he was in one of those two places. When I say these streams are temporally correlated, what I mean is that Bob's location at time t is correlated with or related to his location at time t plus 1. So what the arrows are pointing to here are these correlations, which are drawn as edges. And what these edges are saying is that even though at time t2 and t3 we don't know exactly where Bob was, we do know he didn't change location. So he stayed in whatever room he was in before. OK, so a little more formally. A Markovian stream is a probability distribution over sequences x. So here's one sequence x highlighted in orange. And there's some probability that this sequence is the true path that Bob actually took. So the probability that this is the true path is computed as follows. It's the probability of the first element in the path, so the probability that Bob was in the hallway at time t0, which is 1.0, just times the probability of the remaining transitions in the path, so 0.3, 1.0, etc. Here's another path through the stream. And its probability is computed in the same way. So now because this is a probability distribution, the sum of the probabilities of all the paths in the stream sums up to 1. Here's a formal definition, and this is saying exactly what I just said. So the probability that any path through the stream is the true path is the probability of the first element times the transitions. The reason we call this a Markovian stream is because it adheres to the Markov property, which is that each time step is related directly only to the two adjacent time steps. So for example, you will never see an edge in the stream that goes from t1 to t3 or to t4. So correlations are local, and that's one of the properties that Lahar is able to leverage to do efficient processing. OK, so show you a couple example Markovian streams. We've seen RFID streams. Here's a Markovian stream derived from speech. So I don't know what the actual true sentence was here, but you can see how there's some uncertainty, and the certainty is nicely encoded as a Markovian stream. Similarly, in sensor data, we put these sensors all over soldiers in this example, and at each time step, we're not sure what their activity is. Yes?
So to clarify, if there's a word here, take Thomas, that I could have interpreted as two words, because you can only have one state at a given time, I don't see how that gets handled.
Right. So the time step of a Markovian stream does not have to correspond to like physical time. So in this case, the time step of the stream, the first time step represents the set of possible first words that this person may have spoken, and then the next time step is the set of possible second words that this person may have spoken. Does that make sense?
But if you interpreted Thomas as two words, then if it went to 8 from there, that would be the fourth word, whereas it would only be the third word if you had gone through has.
Correct. So you've caught me. I put this dash up to make things simple. This is not the way a real Markovian stream derived from speech would look. So the first distribution would be Tom versus Thomas. The second would be have versus 8, etc.
Okay.
But most people don't pick up on that, and this is easier to understand at an intuitive level. Yes.
So one way to think, or this is a correct way to think about it. If I had an HMM that I'm using to decode the speech, effectively what we're doing is we're keeping not just the most likely transition, we're having the virtuity decoder sort of keep the top n paths.
Not even the top n, it's keeping all of them. But if you're familiar with speech processing, it's the lattice. This is just a restructuring of the lattice. Yes?
But where are the observation probabilities? I can see the transition probabilities here.
In a normal HMM, you have the transition probabilities, the emission probabilities, and those are constant across time. They don't change. This is what happens to those probabilities when they're conditioned on the evidence. And because the evidence is different at each time, you get, basically the HMM is your prior. You condition that on the evidence, and this is the posterior that you get as the output. Okay. So the reason that I bring these two examples up in the talk is because these are the 3 data sets that Lahar is actually running on back at UW. Okay, so now the remainder of the talk is going to be about sort of the core technical components of Lahar. Some of these things I'll go into in detail, and some of them I won't. Pattern matching is one that I won't, but I do want to explain sort of what it is. So pattern matching is the core unit of analysis in Lahar, like I said. And pattern matching queries are simply regular expressions, or finite deterministic automata. And they're drawn like this. So this query is asking for 2 consecutive time steps in which Bob is first in the hallway, and then he's in the ICU. So here's our Markovian stream. And the output of this query, like we already saw, is a table. And the entry in the table for each time step is what is the probability that this pattern was actually matched in the stream at this time step. So if we just eyeball this stream, forgetting about algorithms for a minute, the pattern is satisfied once at time t1 and again at time t2. So already we know that the probability that Bob satisfies this pattern at any other time is 0. So the question now becomes, how do we figure out what are the probabilities that we actually add in these 2 boxes t1 and t2? What is the probability that this pattern is actually satisfied here in blue? So here's the formal definition for how we do this. And all this definition is saying is that to figure out what the probability is that the pattern is matched at a particular time, we look at each possible path through the stream, take the set of those paths that actually satisfy the query at that particular time step, and sum up their probabilities. So let's look at an example. So in the purple example at time t2, here's one possible path through the stream that actually contains this pattern match. This path has probability 0.15, so we add that to the probability that the pattern was satisfied at time t2. Same thing for this other orange path. The last link has changed, and so on and so forth. So hopefully that makes sense. If it doesn't, we're not going to return to this, so it's okay. These are the semantics of how this table gets filled up, but this is not the actual algorithm that we use to compute these numbers. So hopefully you can see that if we use that algorithm, as the stream gets longer and longer, there are exponentially more paths through the sequence that we actually have to enumerate. So the algorithm I just showed you is intractable. Without going into details, I just want to assert here that there is an O of n algorithm that starts at the beginning of the stream, processes it once, and fills in this entire table. So no time for details, but that algorithm processes about 350 time steps per second, which is more than good enough for real time. Even though Lahar is not a real-time system, it's a warehouse. We process historical data. Okay, so moving on to indexing. The next chunk of the talk is going to be about scalability. So how do we take these pattern matching queries and make them run quickly? The first thing, which I'm going to do most of my detail on, is indexing. So let's go into there. So I said that Lahar has this algorithm that can start at the beginning of the stream, scan it once, and it processes about 350 time steps per second. So even if this is good enough for real time, the problem here is that we have historical archives. We have a massive amount of data. So anything we can do to make this query run faster is going to get us a win. We don't have to wait for data to stream in. So at the very high level, if you think about how to achieve scalability here, we either process fewer time steps or we process them more quickly. Those are sort of the high-level options we have. And indeed, each of those options is something that we've put into Lahar, and they translate roughly to either indexing or approximation. So let's talk about indexing. Okay. In a standard database, B+tree indexes are heavily used, and all these indexes are basically pointers to the tuples in a table, or the time steps in a stream, that satisfy particular predicates. So if we look at this query at the top, this query is looking for a time when Bob is in the stockroom, and then any time later it was in the ICU. The only predicates, or the only states that Bob could be in that actually affect the state of this query are the stockroom and the ICU. So all the time steps when Bob is dilly-dallying around in the hallway don't affect this query. So what we might do is use standard B+tree indexes, just from regular databases work, to identify just the time steps in the stream that actually affect this query. Retrieve only those time steps from disk, and then ignore everything else. So all of a sudden, this will get us much faster processing because we don't have to read all this data from disk anymore. Is there a question? No. Okay. The problem here is that even though these time steps in the middle don't affect the state of the query, they do affect the probability with which the query is satisfied, because the time steps that we remove encode the correlations or the relationship between time t1 and time t8. So we can't ignore them entirely. So what we'd like to do is figure out a way to pre-compute these long-distance correlations and retrieve them at processing time so that we don't have to read all these time steps from disk, but we still preserve the information that's important to us. So the way to do that is a novel contribution in my work, and it's called the Markov chain index. And that's what I'll show you right now. So the Markov chain index is a hierarchical index, so I'm going to build it up across the screen. The bottom level of the index is simply a copy of the Markovian stream. But of course, we don't copy it. We just leave it in place in Lahar. The second level of the index is a copy of the stream, in which every other time step has been removed, and the correlations between each step span twice the distance. So the way we compute these long-distance correlations is that the probability of a link between two endpoints at the upper level is just the sum of all the probabilities of the paths between those same two endpoints at the lower level. And this index just keeps building up. Every level it gets half again as long distance spanning, I guess. Okay, so the index looks like this. Now if we return to our original problem, I'm going to remove the top part. The original problem was we wanted to know the correlations between time t1 and t8 in this instance. Using this index, we can compute this as the product of the three terms in blue. So the product of t1 to t2, t2 to 4, t4 to 8. If we didn't have this Markov chain index to help us look this up, we'd have to read this entire black highlighted portion from disk. So in the end, what this index is gaining us is we can compute these long distance correlations in O of log n time instead of the n time it would take without the index. Okay, yes?
What is the difference with typical data mining techniques on mining sequencing information? Either this is strict sequences or even these are not so strict, like noisy sequences, like some versions of a priori algorithm or something like that. But they could map, you can give him a noisy stream, right? That will come out and generate a probability from going to a state A to a state B, either to another state or directly. Is this something similar to what you're doing?
I'm not quite sure I know what algorithms you're talking about. There's no mining going on here right now. This is just a scalability tool.
Oh, I understand that. Well, what I'm saying is that there are other data mining algorithms in data mining domain that are trying to mine sequencing information.
Absolutely. I don't know. There's not any data mining information that I'm aware of that does imprecise sequential data. There's some time series information out there, but this is a very particular structured type of stream, and I'm not familiar with any other work that deals with this particular type of stream.
Is this squaring the transition matrix?
Basically. I mean, you can think of it that way, yeah.
I mean, how would you compare this against any of the inference? I mean, all I'm seeing you're doing integration, right? You're just summing up all the parts using some of these techniques. So, I mean, have you come across any work in inference? I mean, inference is basically integration as well. And, how would you compare or contrast if you've come across anything?
I don't know of anything. So this is integration in some sense, but it's not inference because we've already done our conditioning on the evidence. So this is just basically.
I mean, it's summing up, right? It's integration. That's not about inference, but it's integration. Right?
It's materializing information that was there, but you didn't have it sort of exposed and materialized and weighted before. So I don't know of any other work that is doing this to achieve scalability, which is the entire point of this.
How about some work in sampling? Markov chain sampling. I mean, this is a Markov chain. And then you need to come up with joint probability distribution across two random variables, which is nothing but integrating out everything else that you don't care about.
Yes.
Right. I mean, those techniques are doing something similar, right?
Yeah. I'm absolutely. The novel claim here is certainly not the computation of these links. This is well known. The novel claim here is that, hey, look, if we actually do this and materialize these different streams at this level, we can achieve log n performance instead of n performance, which I don't think has been, well, I know I hadn't done before. Okay. Blah, blah, blah. Okay, so one slide of experiments to prove to you that I'm not making this up, it actually works. We performed evaluations on this to evaluate the performance of the index using real-world RFID data from the University of Washington. I don't know if any of you have been over there, but we actually have RFID readers in the hallways, and we all carry around little tags, and it's very exciting. So the performance experiments I'm going to show you are derived from both synthetic data and real-world data. In the synthetic data, we actually just synthesized little avatars walking around the building because it turns out people don't like to be tracked for hours and hours on end. And then The real world data is just real people going about their real business for 1 hour. So on the synthetic data, what you see here is on the x-axis, this is the fraction of relevant time steps. So as we move more and more to the right of this axis, more of the time steps are relevant to the query. So the index has less opportunities to skip intervals of data. The y-axis is time in milliseconds. So what you see here is the red line is the naive algorithm that just starts at the beginning of the stream, scans to the end, and it's done. Obviously, because it has to scan the entire stream, this algorithm doesn't care how many time steps are relevant, and we get a flat line. The purple line is the performance using the index. And again, as we move to the left of the axis, there are more and more intervals of this data that the index can be used to skip across, and so we get better performance. So on the real world data, we basically, same axes and everything, same plot, but this is on real world data. So what we did here was we took an hour of a person's data and asked a particular query. So when did Julie enter her office? So that combination of data and query specifies a particular point on the x-axis where this data is going to fall. And that point gets a performance evaluation point for the naive and the indexed algorithms. We did this for lots of hours of data, lots of different queries, and you see exactly the same trend. So the bottom line here is that in practice, you get about 2 orders of magnitude speed up using this index that you wouldn't have otherwise. One little note on this graph, at first we actually thought there was a bug with our system when we saw this graph. So because the x-axis is in log scale here, there's about 50% of that axis that actually doesn't have any queries at all. So this blue circle indicates a big hole in our data set, basically. And we finally figured out that what's happening here is that people are very bimodal. So the points on the left of this circle are questions like, when did Julie enter the kitchenette? I'm almost never in the kitchenette. Most of the time steps in my data are irrelevant. Questions on the right are things like, when was Julie in her office? I'm always in my office, and so almost all the time steps in my stream are relevant. So this is not a technical point. This is more just an interesting observation on human behavior that came out of this work.
So,
yes?
Can you go back? Sorry. So if I read those graphs correctly, there are queries for which actually a full scan is faster than linear.
Sorry.
Right?
Yes. So that's a good point. It happens around 70 to 80% fraction relevancy. So the problem here is that imagine that every time step in your data is relevant. Even when you use the index, using the index is basically overhead at that point. So you have the overhead of scanning the index in addition to reading all the data anyway. The reason I say this is interesting is because it's about 70 to 80% relevancy where this curve actually happens. On a regular index, on a standard B+ tree index, it happens around 10 in a standard data warehouse. So the overhead of even trying to use this index is much lower than the overhead of trying to use a traditional B+ tree index. So. But of course, there are optimizations. I mean, Lahar collects statistics, so it knows when to use this or not based on a given query. Okay, so indexing is one tool that we use to achieve scalability in Lahar. Approximation is another. I'm going to talk about approximation in less depth, but I just want you to sort of know what it is. So if you look at a Markovian stream, the vast majority of the complexity of processing the stream comes from the correlations and the imprecision. Deterministic streams are not nearly this complicated to process. So one of the ways we thought about maybe reducing the complexity of the time to process these streams is trying to approximate these streams in some way. So we asked ourselves, what would happen if we just ignored the correlations? Maybe they're not that important. So when we do that, we get something we call the independent stream, and we call it this because now Bob's his location at time t is independent of his location at time t plus 1.
What's D?
Oh, sorry. D is the size of the domain. Here it's 3. It's the number of possible locations Bob could have been in. In the Markovian stream, each time step requires O of D squared space to store because the correlations have to map between every pair of locations. And in the independent stream, each time step requires only O of D because we just have to record the probability with which Bob was in a particular location at time t. Okay, so this is one way to approximate a Markovian stream. Obviously, we lose some information, but we gain some efficiency, and I'll show you graphs about that in a minute. And we can take this idea one step further and represent the entire Markovian stream using just the most likely path. This goes back to sort of the top K idea of Viterbi. This is exactly what a Viterbi decoding would give you on a Markovian stream. Okay, so I want to very briefly talk about some experiments we did on this. In the RFID domain, we use the same RFID data that I just told you about. So here's what happens. Here's 2 performance plots. The one on the left shows you actual performance in terms of time. The one on the right shows you performance in terms of some measure of error. And the 3 bars show us the 3 different approximations. So as we move to the right on these axes, we're throwing away more information. performance goes up, or time goes down, and error goes up. This is exactly what you would expect. I don't want to go into the details of magnitudes, but it's the right trend. This is what you'd expect. However, if you look at this error plot, this is exactly the same query on exactly the same data, but the query is aggregated in a slightly different way. And all of a sudden, what we see is that the independent error gives us huge error, the independent approximation gives us huge error, and then we throw away more information and get right back down to low error again. So I'm happy to talk about this after the talk. There's a reason for this. I don't have time to go into it now, but if people are interested, we can talk about it later. The main point I want to make here, though, is that when you approximate Markovian streams in this way, performance is affected very predictably. We can predict what happens. But error is sort of all over the place. Error depends on both the query and the characteristics of the data and the characteristics of the approximation you're using. So there's a very rich query optimization story that's happening here. The very bottom line, though, is that what these error experiments have told us is that the Markovian model is valuable. The rich correlation structure of these streams is actually required in many cases to get you appropriate answers. So the complexity of processing these streams is not wasted.
Do you have any analytic control on the error?
What?
Do you have any control on the error? Or you just derive the error empirically?
Oh, no, the control is the Markovian stream itself. So this is the error on what is the difference between the query probabilities that you compute on the Markovian stream versus on the approximate version.
You have bounds, I guess?
There are no bounds. Well, that's not true. There are empirical bounds that you can derive from this, but they are misleadingly bad. They guarantee you that you will be within 99% of your true value. So they're useless. Yes?
The fact that independent doesn't give you good performance on all queries doesn't imply that exists no good approximation.
True.
So have you thought about that, or what's the state of approximate?
The state of these approximations is that the story is complex. We looked at some other approximations, but we have not found an approximation that sort of behaves well, that gives you a nice curve, a nice error curve that goes down as you sort of approximate more and more for every query.
So one thing I noticed is that the examples of queries that you gave us, they are all like order 1 queries, like the dependency is contained in one state. Have you thought of higher order queries, and have you thought of thinking about a model which will go beyond order 1 Markovian problem?
So when you say order 1 queries, do you mean that I've shown you linear?
From hall to ICU. Like how about you, I was in hall, before that I was there.
Yes.
And something like that, like even more complex, right? So your motivation, the talk was actually thinking about higher order queries, but I'm just wondering, have you thought of like, really practically higher order queries and
Yes.
the models that would be required?
Yes. Lahar, so everything I've showed you now is applicable to any regular expression you want. It doesn't matter how linear, nonlinear, whatever. And actually, these experiments here were actually on a fourth order query. So it was basically a query asking for somebody walking down the hallway in 3 different segments and then entering their office.
But still, that's Markovian, right? I mean, anything like that you need to go beyond is a regular expression. And those are the kind of queries I'm asking about.
I see. We have thought about them. They are extremely difficult. The whole reason that this is efficient, we'll see this near the end of the talk. The reason Lahar is able to do this pattern matching efficiently is because the Markovian property means we only need to look at one previous segment of the stream, and the Markovian property of state machines means we only have to look at the current state. As soon as you get into sort of context-free grammars, the state can blow up, and it's not tractable anymore. So no, we haven't done anything with those.
What would happen if your approximation was just to threshold out some of the smaller probabilities?
That's a good question. We tried that. It does behave, you get the right curve, but it's very hard to predict sort of the slope of that curve. So for a given type of data, it's hard to pick the threshold, basically. If you're a user, there's no good way for us to tell you, for this data, a threshold of 0.5 will give you reasonable answers without much garbage. So that's the reason I didn't talk about it here. Okay, so that's all I'm going to say about scalability. We've got indexing and approximation. And the rest of the talk is going to be about analytics. So this is going to be, what can we do beyond pattern matching? We can't do context-free grammars, but there are other additional things we can do besides just processing these regular expressions. So the first thing we can do is aggregation. So in this example, here's our query, when did Bob enter the ICU from the hall? We're very familiar with this. Here's our sample Markovian stream, and here's the output of this query. This is all sort of review. An aggregate version of this query asks, how many times did Bob execute this pattern? How many times did Bob enter the ICU? Because our data is imprecise, the output of this query is a set of possible values for this count and the probability with which that value is true. at first glance, this seems like a really easy problem, right? So at time t1, Bob satisfied this pattern with probability 0.3. At time t2 is 0.2. So what is the probability that Bob actually executed this pattern twice in the stream? Intuition tells us we should be able to multiply these together somehow, but in fact we can't because these pattern match results are correlated. So the 0.3 is correlated with the 0.2. And in this case, not only are they correlated, but they're mutually exclusive. So this pattern and the purple one are mutually exclusive because Bob can't be in two places at the same time. So what I want you to take away from this is that we can't compute the entries to this table as post-processing on the entries to the other table. We have to go back to the raw data to answer an aggregate query. Question?
Are you making an assumption here that the sample of time is high enough resolution that it's not possible that he could have gone back and forth multiple times within a single time step?
Yes, absolutely. And I think that is justified. I mean, garbage in, garbage out. Lahar's analyses are as good as the model you give it. And here in our real-world data, we're sampling once per second. And at the room level of location, that's plenty. OK, so the bottom line here is that even though they seem simple, these aggregate counting queries are actually fairly complex. So let me tell you a little bit about how we process these. In order to do that, I'm going to tell you how we process just the basic pattern matching queries, and then I'm going to go back and show you how we adjust that pattern matching to include aggregates. So to process a pattern matching query, Lahar keeps track of a matrix. So the rows of this matrix are the possible states that Bob is in, the possible locations. And the columns of the matrix correspond to the states that the NFA might be in, the query NFA. So what happens is Lahar starts at the beginning of the stream, fills in this matrix, and then updates the values in this matrix as it goes. And the values in this matrix are just a probability distribution over where Bob is and what the status of the query is. So when Lahar reads the first time step in the stream, Bob is in the hallway with probability 1.0. So our probability distribution has 1.0 probability in the hallway row and in the S0 state because the hallway has triggered a transition, in some sense highlighted in blue, into the S0 state. Now when Lahar goes ahead and moves forward in the stream, it updates this matrix as follows. So it looks at the first edge that says Bob with probability 0.3 moved into the ICU. So 1/3 of or 0.3 of our probability ends up in the ICU row. And because that ICU from state 0 triggers the ICU transition in the matrix, that 0.3 probability ends up in the S1 column of the matrix. OK, same thing happens here. So if Bob follows the purple link into the hallway, then the probability on that link is 0.4. So with probability 0.4, Bob moves into the hallway. And because there's no transition in the query to be triggered by this, that probability sort of by default moves back into state S of the state machine. And the same thing happens with the orange link. So if this doesn't make sense, it's OK. All you need to know is that Lahar is sort of updating this matrix as it goes, and it's a two-dimensional matrix. So now, at each time step, the probability mass in the S1 column, the satisfying state of the query, is the probability that gets filled into the table. It's the probability that Bob actually satisfied this query. So that's regular pattern matching. These are just the regular expressions we talked about. If we do aggregate pattern matching, we do exactly the same algorithm, but instead of on a two-dimensional matrix, we add a third dimension to this matrix. And the third dimension basically represents the possible aggregate values that could be true. So in this case, we have another slice in the matrix moving back into the page for every possible number of times that Bob may have satisfied this query. OK. So this is nice. It's nice because we can use the same machinery for pattern matching and for aggregates. But it's unfortunate because aggregates are actually more complex to process. So in particular, they require n² time instead of n. And the reason for this is you see this matrix. One of these n's comes from the fact that we have to scan the entire stream. And the other n complexity comes from the fact that if this query is satisfied at every time step in the stream, the matrix in the dimension that grows back into the page is going to grow to be size n. And this becomes expensive O of size n to update. The good news is that in practice, it's very rare that a query is satisfied at every time step in the stream. And so the complexity of these aggregates is more, in practice, it's closer to n than n². And also there's work out there, which is not my own work, that lets us approximate this. If this count gets too out of hand, we can just say, what is the expected value of the count, and leave it at that. OK. Without going into any sort of algorithmic details, I just want to tell you there are other aggregates that Lahar also supports. Within a stream, it can very efficiently tell you, did Bob enter the ICU in this stream? If you don't care when, if you just care whether this thing happened, that's very efficient to answer. And Lahar also processes multi-stream aggregates, so aggregates that aggregate together multiple people streams or multiple equipment streams. So for example, how many people executed a particular pattern, Or did anyone come to my talk? Yes. Okay. Okay, so that's aggregation. The last thing I'm going to talk about is work in progress and its drill downs. I'll keep it at a much higher level than the aggregation queries. So the motivation for drill downs is this. The queries I've talked about so far are these basically high-level aggregates. We can look for a particular pattern. We can aggregate together instances of that pattern. But let's say, for example, we want to ask something like this. When did Bob switch between two rooms? He went from a room to a hallway to a room. As an analyst, I ask that query. I look at all these times that I think Bob did this. One of them is interesting. And I want to say, well, what were the actual two rooms that Bob moved between when he did this weird pattern? Why did it take him 8 hours, for example, to go between these two rooms? What were these two rooms? The data tells me that, but the answer to my query that I've already asked does not contain that information. So drill down queries in general are when we want to ask for sort of specific information about the predicates that match a particular pattern. So here's an example query, and here's this data. If we ask what path did Bob take, for example, to get between these two rooms, the answer to this query is actually a subset of the Markovian stream. It's the subset that's highlighted in blue. So already we have a question of how are we even going to return this to the user, and the answer is I don't know yet. So that's one example of a drill down query, what path. Another example is how long did Bob take to switch between these rooms. Another example is what room. This is sort of the one I started with. What rooms did Bob actually move between when he executed this pattern? So the way that these are framed, or the way that I'm framing these in Lahar, is they're basically functions on this blue subset of the stream. So the blue subset of the stream is the portion of the stream that's responsible for Bob actually having matched this pattern. We call it lineage in databases terms, if anybody's familiar with that. And these drill down queries are basically functions on this lineage of the stream. So when we ask what path did Bob take, we're basically asking for the Lahar system to return exactly this blue stream. When we ask what is the length, we're asking for the length of this blue lineage. And we ask for what rooms did Bob switch from. This is actually tricky. I'm not going to go into why it's tricky, but databases people will recognize that projection is very tricky. So projection here is basically asking us to remove portions of this blue highlighted part. And in particular here, we want to remove the parts that correspond to to hallways. But because these time steps are correlated, we can't just start removing hallway elements without figuring out what the correlations are between farther links. Okay, so there's a couple challenges to drill downs. First of all, the answer to the query may be exponential in size. So one of the things I'm looking at is how to either approximate these answers or return just the top k most relevant answers to the user. And another possibly more significant problem is this matrix-based algorithm that I used for both the pattern matching and the aggregates is not applicable here, right? Because the number of possible paths that might satisfy a particular query can be every path in the stream might satisfy a query. And so this matrix grows to the depth of the n. It's intractable. So we need an entirely different computational framework to deal with drill down queries. There's good news. I've made a little bit of progress on this. There is a way to compute this blue highlighted portion, to compute the lineage efficiently in O of n time in a single pass. And then there's two n-squared algorithms that actually let us do the projection. So let us answer the query, what two rooms did Bob switch between? That takes n-squared time. And the current systems issue that I'm working on is between the two different algorithms we've identified for doing this, in each particular instance, which algorithm works better.
So, is this problem for drill down, is it solved for normal relational databases?
Sort of. I named it drill downs to evoke that, but it's not quite the same question. In a normal data warehouse, what you have is you could ask an aggregate query over what were the sales for the entire month of December along certain attributes. Somebody looks at that and says, oh, well, this seems too high. Let's look for each week. That's a drill down. It's when you take some high-level data and you sort of drill down into sort of more and more specific pieces. That is solved, for sure. It's not quite parallel. Does that answer your question?
Yes. So why not? As in, I guess I'm trying to get a handle on what is it about the Markovian streams that makes this problem different from normal precise data?
If you were to try to do that kind of drill down, the warehouse type of drill down with a Markovian stream, I'm not quite sure what that would mean, but maybe it would be easier in sort of a cube-based sense. I don't know. It's different. Maybe drill downs is a misleading name in this sense. I'm not sure how to answer the question. Ooh, sorry. Any others? Okay, well that's the end of Lahar. So the point here is that there's this database. It manages these Markovian streams. Part of the contributions of my work are these scalability tools to make this database run more quickly, and the other part is algorithms to allow sort of richer analyses on these streams. A reorganization of these contributions is as follows. So the conceptual contribution of my thesis is the idea that if we take these Markovian streams and materialize them, put them in a database, that will enable us to do richer queries in an efficient manner without losing the high-level analysis that you get from probabilistic inference. So the technical contributions in this work are scalability tools like indexing approximation, and analytics like the aggregations and drill downs that I just talked about. And then, of course, as a final contribution, Lahar is a running working system. We've got it running on 3 data sets. You can download it from my website. OK, and then in terms of future directions, let's see. So the way I do my work is I look for data management problems in interesting sets of data or interesting analyses. That's exactly where Lahar came from. I'm interested in building systems that actually extract maximal utility from this type of data. So, for example, given a pile of RFID data or given a pile of system logs, what can we do with this data that isn't being done right now? And for me, there are sort of 2 parts to that question. So the first part is, what are the high-level analyses that we want? And usually this involves some sort of imprecise reasoning, because mostly the information you're looking at from data is not exposed explicitly. And then there's a scalability problem. So not only are data sets huge to start out with, but once you start adding in precision, they become much larger. Here are some random examples of problems that I think would be interesting. I found out this morning, actually, that this complex system modeling is actually happening here. So in terms of, let's say you have a data center or a network, and you have some sort of model of how this thing works. Maybe it's a probabilistic model. Maybe you've learned it from data. The question there that's interesting to me is, how do you take this model and make it scalable? How do you build indexes on your historical data so that training that model becomes efficient? As you have data streaming in, how do you update that index to keep it efficiently running? Just stuff like that. So I'm interested in the merger between probabilistic inference and scalability, I guess. That's not really surprising. Before I was working on data warehousing, I did artificial intelligence work. So I do have an understanding of that entire data pipeline from the raw data all the way up to the high-level analysis. But that said, the specific agenda that I work on is mostly going to be driven by the data that I see and the people that I can work with, and so on. So, OK, thanks. Questions?
Any final questions?
So my concern with this type of system is it seems like you've got heuristics in the beginning, which are processing the data, that presuppose the questions that are being asked to some extent. So it seems to have a lot less flexibility than something that stores more raw data. Do you see people change the types of information? So this is really helpful, ideally, in some situation, I assume, where you've got people asking questions that were not anticipated, but that can still be answered using the heuristics that are already in place by the initial processing mechanism. Is that common? What fraction of queries would you say fall into that space?
So when you say heuristics, correct me if I'm wrong. What I hear from that is you're saying, look, this system is only useful on RFID data if people want to ask questions about location. If there's some unanticipated question about the RFID data, you now lost that in the Markovian stream. Is that true?
Right. You're doing some processing. You're dropping some information initially.
Yes.
And
so that's one way to look at it. The way that I would look at that is you're really gaining a lot more. What exactly are you losing? The reason that we have these RFID things deployed is to know the location of the objects. I'm actually making this much easier. I'm providing you with the information that you wanted rather than the information that you sort of have to collect. I don't know. I'd be interested to hear if you have an example of an RFID query that can't be written in terms of location.
Well, let's say after a month of data collecting, we find out that because of the radio frequency properties of some of the walls around, that our heuristic of which room the person was in was actually kind of wrong. And that, it turns out that as people were approaching from the outer hallway, it would turn on for a bit, but when they were in a certain corner of the room, behind a computer where there was essentially interference, that it wasn't collecting data from there. Mm-hmm. We now can't go back and look at our data and try to fix the heuristic so that they can tell us what correct room they were in. We're stuck with this processed data.
No, you're not. You don't have to be. There's no reason, because Lahar is an archive, it's not a real-time system, there's no reason you can't go back and build a new model and produce new Markovian streams that represent that old history. Right? There's no reason you can't do that.
So I guess the question is there any data you lose by presenting your data into a Markovian stream? Is there any information you lose? That's sort of, I think, the crux of these questions.
Clearly,
Sure.
Because I think, okay, then it should be possible that you can go back and redo things. You can come up with an example like that, right?
That you can't go back and redo things?
Yeah, exactly. Because you lose some information. By the mere fact of losing information, you can't go back and reconstruct that.
So you're assuming, so there's a hidden assumption here, which is you're storing both the original data and the Markovian streams. Or maybe you said that and I missed it.
No. That is the assumption that I'm operating under when I say you're not going to lose anything.
Okay.
Surely, if you're right.
Okay.
Right. Are we all on the same page?
So I should be viewing this as a mechanism for which I can take an original data set, do some processing on it, and then answer lots of questions that in a shorter time than I could have answered them if I had issued them as independent queries on the original data set.
Yes, I would look at this as a tool for improving your ability to do data analysis and not a tool for replacing your original data at all. It's a data analysis tool more than it's even a warehouse. The warehousing components are the scalability components that make those analyses efficient. But
So one of the scalability tools that we have whenever we actually analyze a large amount of data is MapReduce. You just basically blast it across a huge number of nodes and you just ask whatever query you want. Lahar is another sort of scalability tool that you're bringing now to the toolbox. How do you compare between the two?
that is excellent. So if I were forced by my advisor Magda to stay at UW for another year and work on this more, I would exactly do that. I would make this a distributed system. I would put it in MapReduce, and I would see what happened. They're completely orthogonal, right? There's no reason. Well, there are some interesting research-related reasons why you can't immediately put this in the MapReduce, but conceptually, sure, MapReduce is a way to parallelize the computation here. The reason that would be difficult is because if you want to parallelize processing across multiple Markovian streams, that's easy because we assume that they're independent. If you have a 5-year-long Markovian stream that you want to run some aggregate query on, now, in order to distribute that, you have to chop it up. And when you chop it up, you lose those correlations, and you're introducing error into your data. So I do think there are ways to chop it up and stitch it together in a way that you don't lose that information, but that would be a research direction.
A lot of what you've described seems to be highly specific to the Markovian stream way of looking at the higher level code. Mm-hmm. What about the things that you've said generalized to different representations? You started off saying there are other representations that achieve the same higher code. They deal with imprecise data, they let you ask arbitrary questions on it. So what about what you've done kind of extends to the bigger picture of things?
So the bigger picture that I'm interested in is taking data and making it useful. So Lahar is one way to do that, right? You take this low level data and you make it useful in that it's fast and easy to write aggregate high-level analyses. The other work I was talking about basically lets you take low-level data and ask high-level queries on it. But if you remember, it basically takes the AI approach. Even the databases people doing this are taking the AI approach. They put a whole probabilistic model into their database, and so then asking a high-level query on the database, what they do under the hood is they build a probabilistic model that actually encodes that query, and they run probabilistic inference inside the database. So we reach the same end goal. We can express largely the same set of queries. Lahar is much, much faster. Because it's pre-computed and materialized this view, it's much, much faster. It's a little bit less flexible. There are some things that you can do more flexibly if you have this dynamic model inside the database. But I think in terms of making this a truly usable system that's going to be effective at producing quick answers, I think this is the way to go.
This is more on, like the choices you made in this project. So, I mean, as far as I understand, you have this Markovian data stream, and on top of it, you have a database system talking to it, right? I mean, why a database system, right? I mean, what is it really getting? Like, what is the advantage? Are there other mechanisms that you have thought of that could have replaced that instead?
I didn't think of other mechanisms, but I don't know what those other mechanisms would be. So the advantages you get from a database are you get the scalability, you get a query language. Lahar has a query language. that allows you in a SQL-like way to ask all these different types of queries. And that's important to be able, I mean, building a graphical model is much, much more difficult than asking a SQL.
I'm not even thinking of graphical model. A very simple scenario, right? I have these Markovian chains, which is nothing but a probability distribution over my sequence. You know, if I have like, million, like a big cluster, I can just, sample from that, like millions of samples, right? And someone asks, hey, how many times did some X happen? All you go and you just count the number of sequences, right? And you can sort of do a simple sampling-based approach. I don't have to go through any of the things, right? I mean, so that's why I was just wondering, right? I mean, what are the different pros and cons if you had thought about at a very high level? I mean, is database the only
well, clearly not.
one way to do it?
You could clearly do sampling. I'm not sure what you're asking. I can give you the pros and cons of sampling.
I mean, if you had to redo this again, would you do it the same way, or are there other things that, retrospectively that come to your mind?
For a single machine system, which is what Lahar is, I would do it this way. So in my experience, when you do sampling, you have to be able to characterize the error, which you can, but the nice thing about this is it's an exact system. Assuming that the Markovian streams accurately reflect reality, you are getting exact information out of Lahar. And to a lot of people, that is important. Once you start doing stuff like sampling, then I think you can become much more scalable, and especially if this were distributed. If you were really trying to get the utmost utility of this information, that might be the way to go. I don't think exact answers, especially for aggregates, I don't think they matter, right? Your aggregate is 5, 5.0, 5.1, whatever.
But on the dynamic staying in this framework, that means you can only deal with Markovian chains. Whereas if I go sampling, I can deal with any order query.
You can, but then you lose the scalability tools like the markup chain index, which is built there is a database called MCDB, which is a database that handles basically any imprecise data you want. It will do sampling to answer any query, but you can't optimize. It's a trade-off, right? How general do you want to be? How fast do you want to be? This is somewhere in the middle.
So one final question from John, and then we take the rest offline.
Would it be easy or hard to answer a question like, how often was Dr. Bob in the same room with the patient?
That gets surprisingly technical, actually. It depends on exactly how you ask that query. So if you want to ask how often, or when did it happen, or how often did it happen, that Bob finished executing a particular query at the same time that Jane did. So when did they enter the room together? That's easy. You just look for each pattern in each stream, and you correlate the times that happened together. If you want to ask something like a query that says, when did somebody leave their office and then enter another office, and you want to know that they executed both of those steps together, that's intractable. So it's provably intractable. So these queries are nicely chosen to be the tractable ones. This was not a mistake, the things I'm expressing.
All right, let's thank the speaker.